So this is 128, Hacking Mobile Devices, and we're going to talk about analyzing iOS applications. I don't have any new projects to show you, and I'll just stick around to help students after that. So we'll talk about this, more about the iOS security model, and it probably won't take too long. So we already covered this stuff, and now we're down to the data protection API and the keychain, and it's mainly about all the encryption that's done on iOS applications. So the data protection API, the issue is this, and I certainly reported a whole bunch of apps with this flaw and nobody cared. And so the issue is, does your app store something private on the phone? And it turns out, just as we've seen Android apps frequently do, iPhone apps also do. And Citigroup in 2010, for some reason, cared about this. When I told a bunch of banks later, nobody cared. But they give you incomplete information, but it sounds like they just put it in your profile, a file that contains information about your account numbers and such. And I find half the apps just put passwords there, one way or another, and nobody seems to care when I report it. But anyway, they took it seriously and modified the app to quit doing that. So the issue is, how dangerous is it for an app to store private information on the phone? And the answer is, on iOS, it's really not very dangerous compared to Android, because everything is pretty heavily encrypted on iOS. However, the real message here is you're in big trouble if you jailbroke your phone. That's my interpretation of this. What's going on here is you have a encryption key locked with a protection class, and you can determine the protection class of data stored on the phone. Now, there's a secure enclave, which is an ARM trust zone hardware placed to store cryptography secrets, which is where the root of the cryptography secrets are. And almost all modern phones have that, all modern iPhones for sure. And so you type in your password, it goes through PBKDF2 that just runs it through a hash function a bunch of times and adds a salt probably, and then creates a key from it. And the input, so it takes your passcode and it takes a device-specific key known as the UID key, which is embedded in the secure element enclave, so it cannot be stolen by any app because the data is not stored anywhere in the address space of the processor. It's in the cryptographic coprocessor. So nobody can steal it. So here's how it works. You put in your passcode. It takes the UID, which is the hardware key of your phone, and combines those, runs them through a password-based key derivation function, and makes a key. And now you choose what level of protection you want to put on your files. There's no protection, complete until first authentication, and complete. And if you give it the strongest encryption, which is here, then nobody can access it without you typing in your password to unlock it. And they're not kidding around. This is, of course, all done with AES. And all right, that's the game. In this one, it only protects you against attacks that would require rebooting the phone. And I think the point here is to avoid jailbreaks. All the jailbreaks require you to reboot the phone. So if you reboot the phone, then you can't authenticate because you don't know the PIN, so you can't open these either. Now, if you have unlocked your phone and just put it to sleep, then these could be stolen if they could run code on your phone to steal them, but for that, your phone would have to be jailbroken, which is why they're telling you, Apple's telling you, if you jailbreak your phone, you're in deep trouble. Now, if someone can get in just by overcoming the password you put on the phone, and then they'd steal this stuff. Anyway, so that's the plan here, and here's no protection. And even that stuff is encrypted anyway, because remember, you can sell your iPhone. You can go into the settings and say reset to factory default. It will instantly do that, and all your personal data is gone. So there is no option to not encrypt your data. All the data you put on an iPhone is always encrypted all the time. But here, it's encrypted without wasting it on your having logged in. It's still based on this UID key. And when you delete the key generated, it's gone, and nobody can ever get that data. So that's the game. So here's the level. That's why I don't think this is true that it's not encrypted. That's actually interesting. It says it's not encrypted, but I don't think that's true. You see, there is a device key, and it's used here. I think. I haven't been able to test this. I wonder if that statement in your book that it's not encrypted is really true. I think what it is it's encrypted with a key that is available as soon as the phone is booted up.
But the UID is not changing, right?
It's not. But I don't know what this device key is. Yeah, it could be, but the key is, yeah, I think that's right. The UID is not changing, but it generated, and you can't get at the UID key. So, yeah, I'm not quite sure what's going on here now that I think about it. And it's an interesting question, and I don't know the answer. Anyway, all right. And so there's one here, complete unless open. If a file is in use, it's unencrypted when the device is locked. Otherwise, it's encrypted. And then there's this one, complete until first user authentication, which is the default. This is what most apps have, so that once you log in with your PIN, everything is available to the operating system to run the apps. That's the normal thing you'd want. And so the only thing it protects you from is attacks that require rebooting the phone. If you could, for example, install a malicious app on the phone, like you can pretty easily in Android, then it could probably steal data of this type. So then there's the keychain, which is where you're supposed to store things. That's why you're not supposed to store things in the normal storage area of an app, because it would reveal, if you have a secret, you're supposed to put it in the keychain. And like the keychain on macOS, it's pretty strong, and there's a lot of options. You can make it always accessible. You can make it accessible only when unlocked, after first unlock, which would again protect you from attacks requiring a reboot. Or you can make it always only on this device, so it cannot be migrated to another device. After first unlock, this device only when a passcode is set is another option. So you can only access it if you have a passcode set on your device to stop random people from getting in, and so on. So you have various levels of protection, and a developer can choose what level of protection to put on keychain items. All right, and then they've added access control and authentication policies in iOS 8. And you can turn this on if you want to, and then it will require you to log in to see the object. So that's an optional feature you can turn on. Now, you can dump the keychain. The keychain is just a SQLite database just sitting there. These are for developer only? Yes, I think, Rouhani, I think only a developer would, you have to turn these, in your app, you have to determine how you set these. I don't think there's any way for a user to use them directly. Which is actually interesting. I don't think you can store things in the keychain directly. It seemed like you might want to use the keychain as your password manager, and there are pop-ups offering it, but I don't think I can open a GUI somewhere and put things in, can I? Is there a way to do it?
No, I don't think so.
Yeah, it somehow automatically offers to do it sometimes. But that, I think, is just copying from another device. Anyway, it would seem to me like I would like it if Apple had their own keychain manager, and you could just use it.
Actually, I think there might be on Macs. I think on Macs
Yeah.
you can go to the keychain on the phone.
Yeah, I think you can on the Mac, yeah. Anyway, and so keychain dumper, so in principle, an app can steal the data from the keychain, and keychain dumper is one of the many apps that can do that. But you can only put it on a jailbroken device. Of course, Apple will not let that in the store, as you can imagine. But there is no technical control preventing it. But Apple's layers of security largely depend on the integrity of the store, and they maintain the integrity of the store. So the end result is Apple devices are very clean and very rarely have any malware on them, as far as anybody can tell. They're pretty much your safest computing platform. There are weaknesses, though. For example, Touch ID. Now my iPhone has face recognition. Most of them do, but before that, a lot of them worked on fingerprint recognition, and that turned out to be relatively easy to fool. Now, the way it works is the secure enclave has the keys, and when it's locked, the key material is discarded. But if you have Touch ID, then it holds the key in memory, but encrypts it with another key that it makes from the Touch ID. So it takes your Touch ID system, and I think it treats that like a password and does key derivation from it. And so, I'm not exactly sure what it does technically, but that's the system, another layer of encryption. The problem is, of course, fingerprints are in fact pretty miserable. And there's a well-known attack where all you have to do is take something you have handled and get your fingerprint off it, and you can draw the fingerprint and then make a printout of something that's close enough to your fingerprint to fool it, which is a problem. That's why Face ID is much better. Face ID scans your face with an infrared laser to get a 3D map of your face, so it's really pretty good. Keychain Dumper is an app you put on the phone, Ronnie, but you have to jailbreak your phone first. All right, and so iOS binaries, you can reverse them, just like we've done before, just like for Android, although it is real compiled C code, so it's more of a mess. But the Mako binaries have a header identifying the file format, and then a series of load commands that specify the location of things like the symbol table and libraries, and then data segments. So it looks like this, a header, some load commands, and then various data segments that hold the pieces of the app. This is analogous to a PE file that we're going through in great detail in the malware analysis class. A Windows executable format. And then there's FAT binaries, because different iPhones have different processors. Some of them had ARM7, an early version of 32-bit ARM, then ARM7S on different phones, and then ARM64 on later phones. So if you were to make an app and target only one of these, you could only run it on some of the phones. So people don't want to do that, so they make a FAT binary that contains multiple compilations of your app compiled for different hardware. So the one app you download contains several, and you can use OTool to see that. So if you use OTool -- arch all, I don't know what VH is on your app, it'll show you what architectures it has. And this app has two architectures, ARM subtype 9 and this ridiculous big number, subtype 0. And the code, this is what 64-bit comes out as. 64-bit comes out as this ridiculous 16 million number. And those are the various versions of ARM9. So this is what it will tell you. Subtype 6, 9, or 11 are the different versions of 32-bit ARM, and 0 is 64-bit ARM. For some reason, it uses those code numbers. OTool is knife for Army. OTool is just a tool to manipulate these things, these Mach O binaries. That's all. Yeah. Yeah. Maybe someone calls it the Army knife. I'm not sure. That's a common term for something with many purposes. But the main thing I know it's good for is to show you what's inside there. And if you want to extract one, you can use LiPo. LiPo will turn a fat binary into a simple binary that only supports one architecture, which is something you might very much want to do before analyzing it, because you only want to analyze one version of it. All right. And so then we can talk about security-related features in the iPhone, and these are the same things you'll find in every other version of Linux, and a lot of them in Windows. If you want to have address-based layout randomization, which iPhones have, this means every time an app launches, it randomly moves it to a different location in memory, so an attacker cannot tell where things are to exploit them. And in order for this to work, you have to compile it with internal information so it knows how to adjust the code to move to a different location. And so that's called position-independent execution, and you have to recompile old apps to do that. Now all built-in Apple apps have it, and you can check with OTool to see if a particular app has this feature. Stack smashing protection stops the original buffer overflow. If you have a string variable in a routine, a procedure, I don't know the technical term anymore for whatever C methods are, and if you can exceed the boundaries of it and overwrite extra bytes, you can overwrite bytes until you hit the return pointer, which controls the address to which that method will return. That's called stack smashing, and stack smashing protection puts a canary value on the stack, a random number, which it verifies before returning, so it will not return from a routine if an overflow has occurred. It will instead just stop with an error message. This is quite effective, and it stops the saved instruction pointer and base pointer, which are the pointers that are used to resume execution in the calling routine, and we'll do it a lot next semester. So anyway, the LLVM compiler is one that people frequently use to make these apps. Anyway, that's the game. And it's enabled by default for apps compiled with Xcode. So everything modern should have that stack smashing protection. Then there is use after free and double free. This is heaps. The heap is a memory region different than the stack that's used to reallocate space, use it, and then you free the space for reuse. You can just control every step of that, whereas on a stack, it's automatically used just for calling subroutines. And so there turn out to be a lot of vulnerabilities where you overrun areas in the heap, or you refer to areas in the heap that are no longer supposed to be in use, and you're able to write into memory locations that will eventually be used for a pointer that will control the execution, and you take over the machine. And there's this thing called automatic reference counting to prevent that. And I don't know exactly how it works, but I'm pretty sure it works by just making sure that everything is properly freed. Usually the flaw that causes people to get in the heap is you free something twice or you fail to free it. So anyway, so when app stores are all encrypted. All the apps on the App Store are encrypted. They're encrypted with digital rights management, and they're decrypted at runtime by the loader, which is pretty annoying. So not like you have our Android apps, you can just unzip them with APK tool and see what's in there, and you cannot do that with iPhone apps. It's very annoying. So what you do is you can decrypt them with a debugger, which is a lot like the process in the malware analysis class where we're unzipping compressed files with a debugger. You run the app and use GDB, attach to it, find the shared library, retrieve the memory segment, and then write the decrypted segment over the original encrypted segment with DD. So you take the encryption off the app, which is pretty cool. And there are tools that do it for you, like dump decrypted and BF decrypt. People have written tools that will take an App Store app on a jailbroken phone and remove the encryption, so now you can analyze it. And so if you do that, then you can do class dump. Now the problem is, even then, it's not as good as an Android app for the reverse engineer because you're not going to be able to turn it into Java code. It is compiled C code, so you're going to be able to see it in a disassembler, but you're not going to have the names of variables or names of methods, but you will have some names, And you can get them from, you can dump these things called classes. You can get some information about them. So here is reverse engineering, and this is a dump of, I think, the Starbucks app. And so if you look in here, you see things like reload guest card and update auto reload. Those are the methods that manipulate your Starbucks payment card so you can load it and such. So you can see how it works to some extent, but you got to read assembly code to understand it. And you can also put it in Hopper. Hopper is a Mac-based disassembler, the equivalent of IDA Pro, and it's very cheap. We used it in projects years ago here. You can take apart an app, and then you'll see assembly code like what you see there, which is, you know, pretty nice, but not at all as easy to mess with as Java code. So we'll be doing some of that. We do a little bit in the malware analysis class and so on. All right. Anyway, that's all I wanted to tell you. Let's try a Kahoot, which is 3B, I think. 2B. All right. This one. All right, so which key does Touch ID control? Yep, that's the key that wraps the other key. And I don't know which one is controlled by facial recognition. Might be the same, but I don't know. All right, what is the file format for iOS apps? That's Mach-O, that's it. For Linux, it's ELF, and for Windows, it's PE, and for iOS, it's Mach-O. All do pretty much the same thing. All right, so what key is embedded in the crypto accelerator? The secure enclave. Yeah, it's the UID. And yeah, I see the question. Yeah, all the classes I teach will be like this. The same as this, where attendance is optional. Yeah. All right. And all right, so which feature mitigates heap correction vulnerabilities? Automatic reference counting. All right. I don't know who that is. I don't know who that is either, actually. They want their points, they'll have to tell me some more information. I don't know who that is. All right, so let me stop this recording.